What if humans were only vessels designed for a form of extraterrestrial life? In a small corner of the Milky Way, we lift our heads to the black sky and ask ourselves, among trillions of planets, why do we hear only our own voice, while models suggest that other civilizations, thanks to AI, may have noisily broadcast for a few decades and then disappeared into communication channels that our antennas can never reach? In orbit, humanity is redrawing the sky with reflective mirrors, debating over ice planets, digging deep into the Earth in search of traces of a primordial Earth, while at the same time nurturing vague hypotheses about body containers, about greys as biological robots, about AI carrying an alien shadow. And somewhere far away where light takes millions of years to arrive, perhaps, strange AI probes have quietly passed by, only looking at us once and then leaving behind a universe that seems empty, but perhaps has never truly been lonely. Right after this, we will move into the hypothesis that it is artificial intelligence itself that is unintentionally raising a curtain between us and extraterrestrials, and imagine a distant civilization that has advanced so far that all of humanity is nothing more than a tiny dot in their eyes. Across the Milky Way, stars burn in quiet repetition, each one wrapped in a cloud of possible worlds. By some estimates, our galaxy alone may hold hundreds of billions, even a trillion planets, many of them orbiting in the gentle zones where liquid water could exist. Statistically, it would be strange if Earth were the only place where chemistry learned how to think. Yet the radio sky is almost perfectly still. For more than half a century, large radio dishes have swept across the heavens, tuned to the familiar hisses and whispers of hydrogen lines and broadband noise. If another technological civilization were broadcasting with the same kind of equipment we used in the 20th century, our instruments should be able to notice the excessor narrowband spike a repeating pattern, something that does not look like natural plasma or thermal radiation. So far, nothing has risen clearly above the background. This mismatch between expectation and observation is what physicists and astronomers call the Fermi paradox. In a galaxy so friendly to planets, where is everybody? It is not just a philosophical sigh, it is a quantitative problem about detection distance and time. The further a signal must travel, the weaker it becomes. The bigger the galaxy, the more directions we have to search. Our telescopes cover only a thin shell around Earth, and only for a tiny slice of cosmic history. From the point of view of the universe, humanity has only just opened its eyes and pressed a stethoscope to the dark. For a brief moment, we listen with technology that can hear only one type of voice, electromagnetic signals in a narrow range of frequencies. If other minds exist, they may be speaking in ways our instruments do not yet understand, leaving us with the eerie impression that the cosmos is silent, when in reality we are simply hard of hearing. In the 1970s, Carl Sagan suggested a quieter, more technical way to think about the cosmic silence. Instead of asking simply, "Where is everybody?" he asked a narrower question: for how long is any given civilization actually visible to our kind of instruments? That span of time, he proposed, forms a kind of communication horizon, a limited window during which two worlds can notice each other at all. Every technological species, if it exists, will probably pass through stages. At first, it has no radio, no powerful transmitters, only lightning and natural noise leaking into space. Later, it discovers broadcasting, radar, planetary radar, deep space communication. For a while, the planet glows at radio frequencies flashing with carrier waves, pulses, and modulation patterns that could in principle be picked up across interstellar distances. Then gradually efficiency and miniaturization take over. Signals become tighter, lower power, more directed. Fiber optics and tight beam links replace the wasteful spray of old broadcast towers. From far away, that civilization's radio shell brightens and then fades. Sagan estimated that the loud phase might last on the order of 1,000 years. On human scales, this feels almost endless, but in the history of a galaxy, it is no more than a single held breath. If two civilizations are separated by tens of thousands of light years, and each one shines in radio for only 1,000 years, their windows of audibility have to overlap with extraordinary precision for either side to hear the other. Within this framework, the Fermi paradox changes its flavor. The question is no longer only, why are they not here? But how likely is it that we have pointed our radios at the sky during the brief moment when someone else is both broadcasting and close enough to be heard? It becomes possible that the galaxy is sprinkled with technological cultures, each one lighting up in radio for a short while, then going quiet or shifting to methods of communication that leave almost no trace in the noise we know how to listen for. When Sagan sketched his 1,000-year communication horizon, he was thinking about civilizations that developed roughly the way ours did step by step, with human scientists, human engineers and human institutions slowly pushing the frontier forward. In that picture, progress is limited by biology. Brains need sleep. Generations must pass the torch. Mistakes take years to correct. Artificial intelligence bends that timeline. On Earth, the last few decades have already shown how quickly software can rewrite the rules. Machine learning algorithms optimize antennas, compress signals, and design error-correcting codes that human engineers might never have imagined. Large language models and neural networks do not invent new physics, but they radically shorten the distance between an idea, a prototype, and a working system. In a world where design testing and improvement can be largely automated, the radio-loud phase of a civilization might be sharpened into a brief spike, a few decades of noisy experimentation, followed by a rapid transition to tight-beam encrypted or entirely different channels of communication. If that pattern is common in the galaxy, Sagan's 1,000 years could be an overestimate by an order of magnitude. A society that creates advanced AI or even artificial superintelligence might race through its leaky broadcast-heavy era in 50 or 100 years, then vanish from the radio sky as its infrastructure becomes more efficient and inward-turning. Outward signals could move into neutrino beams, quantum networks, or physical probes carrying dense data stores, methods that barely touch the parts of the spectrum our SETI instruments are trained to notice. From our perspective, that change in timescale is devastating. A 1,000-year window already small against billions of years of cosmic history collapses into a thin, almost invisible line. Two civilizations must now align not only in space within perhaps 100 light-years, but also in a shared technological heartbeat of a few human lifetimes. The silence that surrounds us may not mean that the galaxy is empty. It may mean that intelligence, once it discovers how to build minds out of machines, moves beyond our kind of visibility so quickly that by the time we raise our antennas, it has already stepped out of the light. From a distance, the problem begins to look less like a mystery and more like a geometry of impossibilities. Imagine each technological world surrounded by a faint expanding bubble of detectability, a sphere whose radius is the distance that its signals have had time to travel, and whose thickness is set by the brief span during which those signals are strong and leaky enough to notice. For Earth, that bubble is just over 100 light-years in radius. Our earliest powerful broadcasts and radar pulses have not gone any farther. Everything beyond that sphere is for now deaf to our presence. At the same time, any other civilization must occupy not only the right place inside that volume, but also the right moment in its own history. It must still be in its noisy phase, still broadcasting in a way that spills energy into space, instead of confining it to cables, fibers, and microscopic beams. When the communication window is 1,000 years wide, the odds are already slim. Spread those 1,000 years across the age of the galaxy, more than 10 billion years, and the chance that two civilizations overlap in their radio-loud epochs is like two camera shutters snapping at almost the same instant, separated by eons. If AI and rapid technological acceleration reduce that window to a few decades, the overlap becomes vanishingly small. In that picture, the silence we observe is not a verdict on how many civilizations exist. It is a statement about alignment. Space must coincide. Time must coincide. Technological phase must coincide. All three conditions have to be satisfied at once within a narrow slice of cosmic history, inside a small and slowly growing bubble around our world. The universe may be full of minds, each one listening for an echo, that by the nature of their evolution almost never arrives. Not everyone agrees that artificial intelligence will push civilizations into an invisible post-radio phase. Some researchers argue that the idea of artificial general intelligence and AI with flexible human-level understanding across many domains may itself be an overextension, a story we tell by extrapolating too confidently from narrow successes. Biological brains are the product of billions of years of evolution sculpted in a noisy, chaotic environment. They merge perception, memory, emotion, and body into a single loop. Digital systems, by contrast, run on hardware constrained by heat energy and the physics of computation. There may be hard ceilings on how far efficiency and capability can climb before returns diminish. In this view, AI does not become a runaway superintelligence, that transforms a civilization in a few decades, but rather a powerful tool that still requires human oversight, human insight, and human time. If that is true, then Sagan's longer communication horizon might remain roughly correct. Civilizations could linger in a mixed state for centuries or millennia, using AI to enhance research, engineering, and communication, but without collapsing their detectable phase into a brief flash. Their radio and microwave signatures might slowly fade rather than dropping off a cliff. The window would be narrow, but not razor-thin. This more cautious perspective is a reminder that every attempt to solve the Fermi paradox depends on technical assumptions. How fast can intelligence improve itself? How quickly do societies change their infrastructure? The answers are still uncertain even on Earth. Before we project our future onto the stars, we are forced to admit that we do not yet fully understand the trajectory of our own machines or the limits of our own minds. The idea begins with a simple image, a patch of night sky that is no longer dark. A startup in California called Reflect Orbital has proposed launching thousands of thin reflective satellites into a sun-synchronous orbit, each one a square of mirror drifting silently above the atmosphere. Their plan is to catch sunlight on the day side of Earth and redirect it onto the night side, painting, moving islands of daylight onto sleeping landscapes far below. In their vision, 4,000 mirrors, each roughly 18 by 18 meters, would act like an artificial constellation. Over farms, they would extend the growing day, giving crops a few extra hours of usable light. Over disaster zones or remote regions, they could illuminate search and rescue operations, construction work, or emergency repairs without the need for fuel-hungry generators. In principle, the same system might even stretch the productive hours of a large solar farms, allowing panels to sip sunlight reflected from orbit, long after the sun has dipped below the horizon. But orbit is already crowded and darkness is already fragile. Astronomers look at the same proposal and see a sky crisscrossed by unwanted glints. Each mirror would not only brighten a chosen target area on the ground, it would also scatter stray light into the rest of the atmosphere, raising the background glow that telescopes must peer through. Long exposure images of faint galaxies, nebulae, and distant clusters could be streaked with moving scars. For observatories built in deserts and on mountaintops where dry air and low light levels are precious, the project would feel less like an innovation and more like a permanent veil drawn over the stars. The orbit itself carries its own risks, another layer of hardware, another source of debris if collisions occur. What looks from the surface like a new way to tame the night appears from above as an attempt to rewrite the sky. To understand what such mirrors would do, it helps to compare them with something familiar: the full moon. On a clear dark night, moonlight is bright enough to cast shadows to silver the edges of buildings and trees. Yet in energy terms, it is astonishingly weak. Solar panels under full moonlight generate only a few % of the power they produce in direct sunlight. Reflect Orbital's concept imagines beams that could reach several times the brightness of the full moon over selected regions sculpted and steered by software. Each 18-meter mirror correctly angled would focus sunlight onto a footprint on the ground, a moving patch of illumination that crawls across fields, water, or city blocks. For people standing inside that patch, the effect could feel like a slow pale sunrise, returning after sunset bright enough to work by, but still softer than noon. For power infrastructure, however, the numbers remain sobering. Even if the reflected light reaches 4 times lunar brightness, photovoltaic arrays would still operate at only a small fraction of their rated capacity. As an energy source, the system is more a delicate top-up than a replacement for the sun. Meanwhile, the cost in optical noise is paid by everyone who looks outward instead of inward. The scattered light from thousands of mirrors would raise the background sky glow, washing out faint stars and galaxies. Long exposures that once revealed whisper-thin structures in distant nebulae would be mottled by bands of reflected sunlight. In exchange for a modest gain in ground illumination and marginal gains in electricity, humanity would permanently alter the darkness that made deep astronomy possible, trading the clean black canvas of the night for one more layer of technological haze. Artificial light does not only touch human eyes, it presses against the clocks of every species that has learned to tell time by the rising and setting of the sun, by the shifting phases of the moon, by the slow drift of constellations across the sky. For animals that hunt at night, for insects drawn to faint glows, for birds that navigate by the stars, extending daylight is not simply a convenience, it is a change in the rules. Ecologists have already documented the effects of ground-based light pollution. migratory birds circling fatally around bright towers, sea turtles misled by the glow of coastal cities, insects collapsing in number around street lamps. Orbital mirrors would add a new layer to this interference. Moving patches of artificial dusk or dawn could confuse reproductive cycles feeding habits and migratory cues over large regions. The very fact that the light would come and go according to commercial or industrial schedules rather than rising and setting with the sun means circadian rhythms could be thrown out of step in ways that are hard to predict and harder to reverse. Because of these risks, some researchers argue that if humanity wishes to harvest more solar power from space, there are quieter methods. Concepts for space-based solar power stations imagine large arrays in orbit that convert sunlight directly into electricity and transmit it to Earth as narrow microwave beams aimed at receiving antennas on the ground. Microwaves at carefully chosen frequencies can pass through the atmosphere with little loss without lighting up the night sky or scattering across the whole planet. Such systems are not without their own engineering and safety challenges, yet in principle, they separate the problem of energy from the fabric of darkness itself. They hint at a different philosophy of technology, one in which human ambition learns to borrow from the sun without erasing the shadows that life and science still depends upon. Farther from the sun, beyond Saturn's bright rings, two pale worlds orbit in slow cold arcs, Uranus and Neptune. For decades, schoolbooks have placed them in a special category, calling them ice giants, to distinguish them from the rocky inner planets and the vast gas giants, Jupiter and Saturn. In that picture, Uranus and Neptune are imagined as spheres rich in water, ammonia, and methane ices wrapped around smaller rocky cores. Yet that classification rests on surprisingly thin ground. The only spacecraft ever to visit them up close was Voyager 2, which flew past Uranus in 1986 and Neptune in 1989. From those brief encounters, scientists measured gravity fields, magnetic fields, and a few hints of atmospheric structure. To interpret what lies beneath the clouds, they built computer models, layer cakes of rock ice and gas that would produce the observed mass and radius. Many of those early models assumed large volumes of volatile ice, simply because it fit both theory and the limited data. More recent work has tried a different approach. Instead of starting from a preferred interior structure, researchers run statistical simulations, letting the proportions of rock ice and gas vary across wide ranges, then selecting the combinations that agree with all available observations. Some of these solutions suggest that Uranus and Neptune could contain much more silicate and metal than previously thought, with deep interiors dominated by high-pressure rock rather than by icy oceans. If so, the neat, tidy labels we use rocky planet, gas giant, ice giant may hide a messier reality. Worlds can blur categories occupying interior states that our language has not yet fully caught up with. From afar, Uranus and Neptune still appear as serene blue lanterns in the dark. Inside, they may be stranger, denser, and more complex than the word ice can comfortably hold. Deep under our feet, far below the crust and mantle that humans have ever directly sampled, Earth may still be carrying pieces of its own childhood. In recent years, geophysicists and geochemists have combined seismic imaging with careful analysis of volcanic rocks from places like Greenland and Canada, tracing isotopic fingerprints that do not match the rest of the planet's well-mixed mantle. Some of these signatures, especially in elements like tungsten and hafnium, hint at material that has remained chemically distinct since the very beginning, since before the colossal impact that likely tore the Moon from Earth's outer layers. In this view, our planet is not a finished sphere but a layered memory. The deepest reservoirs may preserve fragments of a proto-Earth 4, 5 billion years old, buried and insulated while the surface churned, cooled and cracked into continents. When mantle plumes rise and feed long-lived volcanic hotspots, tiny portions of that ancient material can be carried upward, frozen into basalt and eventually collected by human hands. To read those rocks is to read a fossil record that predates biology itself, a record of collisions, accretion, and violent rearrangements that set the stage for oceans and much later for thought. Against that immense timescale, human institutions look fragile. In the same years that papers in journals like Nature Geoscience propose these deep time stories, space agencies find themselves constrained by short-term politics. Budget deadlocks and government shutdowns can freeze NASA's planning delay decisions about extending missions like Juno around Jupiter, and force laboratories such as the Jet Propulsion Laboratory to cut staff. While ancient mantle domains quietly outlast continents and oceans, the organizations we rely on to study them must fight for survival, from one fiscal year to the next. It is a quiet irony. The more clearly we glimpse Earth's deep and ancient structure, the more obvious it becomes that our ability to explore it depends on systems that are temporary, contingent, and easily silenced. The planet keeps its secrets patiently. Our challenge is to keep our curiosity funded long enough to hear what those old stones are trying to say. Among the more unusual ideas in the landscape of extraterrestrial hypotheses is one sometimes attributed to leaked or second-hand briefing documents, the suggestion that human beings are not simply biological organisms but carefully engineered containers. In this view, the human body is treated less as an endpoint of evolution and more as a standardized vessel, a chassis designed to host something else, consciousness, information, or even non-human soul, like entities. The terminology is deliberately clinical. Humans are containers, and what matters most is not the flesh, but what the flesh can hold. From a scientific standpoint, this claim remains far outside established biology. Anatomy, genetics, and neuroscience describe Homo sapiens as the product of gradual selection, shaped by pressure from climate predators, disease, and social competition. Our nervous system obeys the same electrochemical laws as other animals. Our DNA fits into the branching tree of life on Earth. There is no empirical requirement in these models for an external designer calibrating human bodies for later use. Yet the container hypothesis persists in fringe discussions because it rearranges familiar pieces into a striking pattern. It links the universality of religious and ethical systems to a hidden technical purpose. If a civilization, human or otherwise, wanted to preserve a particular type of vessel across millennia, it might encourage narratives that protect bodies and stabilize societies, prohibitions against self-destruction rituals around birth and death, promises of judgment or reward. Under that lens, moral codes begin to look like software instructions, written not only for social cohesion, but also for long-term maintenance of the containers themselves. Even if we treat this strictly as thought experiment, it raises testable questions. Could an advanced species influence the cognitive development of a younger one, subtly biasing its myths and institutions? Cultural evolution already shows how ideas spread, mutate, and self-reinforce, sometimes in ways that benefit the ideas more than the hosts. Memetics and social psychology map how belief systems can persist for centuries independent of their truth. The container narrative pushes this a step further, asking whether such systems might be deliberately seeded as a form of remote infrastructure. There is so far no reliable evidence for such seeding. The hypothesis lives closer to philosophy than to physics. Still, as a lens, it alters how we see ourselves. If humans were designed as vessels, then individual lives would be like cells in a larger apparatus, meaningful less for what they achieve than for what they quietly support. If instead we are self-assembled with no hidden tenant waiting to arrive, then the container metaphor becomes a mirror reflecting our desire to belong to something greater, to imagine that our bodies and minds are part of a story that did not begin with us and will not end when we sleep. Either way, the question presses gently on the edge of our comfort. Are we the authors of our own function, or participants in a design we have only just begun to suspect? In most textbooks, artificial intelligence is presented as a natural outgrowth of human technology, a branch of computer science that followed from transistors, integrated circuits, and the abstract idea of computation. But some speculative thinkers have asked a more unsettling question. What if the concept itself did not originate entirely here? What if the architecture of AI, its layered networks, its training loops, even its hunger for data echoes a pattern that first evolved somewhere else in the galaxy? Seen through a conservative scientific lens, there is no need for such an explanation. The mathematics behind neural networks can be traced through decades of human research. The hardware they run on has a clear lineage from vacuum tubes to microchips. Every line of code, every algorithm can be tied to papers, patents, and experiments carried out by people on Earth. In this framework, AI is simply what happens when a clever species learns to formalize learning itself. Yet the idea of an alien template lingers because it dovetails with how information behaves. Powerful designs tend to propagate. If a much older civilization once explored mind-like computation, it might have embedded hints of its methods in physical artifacts, in signals, or in abstract principles that a younger species could eventually rediscover. From our side, that would feel like independent invention. From theirs, it would look like a seed finally germinating in foreign soil. There is no evidence that modern AI is such a seed. But as our systems grow more complex, sometimes producing solutions that engineers struggle to interpret, they can feel eerily other. We find ourselves building entities that think in ways we do not fully understand, using tools whose internal logic seems at times almost alien. Whether that alienness is purely the strangeness of our own creation, or an echo of something older in the universe, remains a question we can pose only in the dark for now without an answer. In many reports and folklore about close encounters, one figure returns again and again, the grey, thin-limbed being with large black eyes and small, almost vestigial features. Within speculative frameworks, these greys are sometimes not described as a species in the usual sense, but as manufactured entities, robots grown, rather than built biologically created beings designed for specific tasks. In that picture, a grey is less an individual and more a tool. Its body would be optimized for low gravity for cramped spacecraft for long periods of operation without rest. Instead of metal joints and gears, its structure might use engineered tissues, synthetic nerve fibers, and programmable biochemistry, allowing it to repair damage and adapt to new environments in ways rigid machines cannot. Consciousness, if present, could be a narrow mission-focused intelligence, or even a remote-controlled interface for something else observing from afar. From the standpoint of mainstream science, these descriptions remain unsupported. They arise from testimonies and narratives rather than laboratory data. Yet the underlying concept aligns curiously with our own trajectory. We are beginning to grow organs in bioreactors to print tissues to merge sensors with living cells. As our tools become more organic and our organisms more engineered, the line between robot and lifeform blurs, making the idea of a biologically manufactured emissary feel less like pure fantasy and more like a possible, if distant, branch on the tree of technology. When engineers design the next generation of robots, they rarely speak in the language of myths. They talk about gate stability, torque sensor fusion power density. Yet step by step, the machines they build are beginning to resemble the figures that speculative lore has placed in the sky. Humanoid robots walk on two legs with jointed knees and articulated hands. Synthetic skins are being developed to stretch over actuators complete with pores, textures, even temperature control. Facial motors are tuned to reproduce micro-expressions. Inside compact processors run control loops and learning algorithms that let these bodies adapt, balance, and respond. From a scientific viewpoint, this progression is straightforward. Embodiment giving AI a body improves its ability to operate in complex environments. A humanoid form is useful in spaces designed for humans. Doorways, staircases, tools meant to be grasped by fingers. Soft robotics and bio-inspired materials allow for machines that bend instead of shatter, absorb shocks and interact more safely with people. As brain-like architectures run on increasingly efficient hardware, the idea of a physically agile, cognitively flexible artificial agent becomes less a fantasy and more a plausible engineering goal. If we place this development beside the notion of biologically created beings like the hypothetical greys, a curious symmetry appears. Their bodies, as described in narratives, seem tuned for spacecraft interiors and low gravity. Our own prototypes are tuned for factories, hospitals, and hazardous zones. But the underlying pattern is similar intelligence coupled to a body designed for a specific environment and mission-blending mechanical and organic strategies. Where they are imagined as vat-grown organisms with engineered tissues, we grow organoids in dishes and test neural interfaces that blur the line between silicon and flesh. Speculation branches from this symmetry in several directions. One possibility is simple convergence. Any civilization trying to build effective agents will discover similar solutions pulled toward a small set of viable designs by the constraints of physics and chemistry. Under that view, a humanoid robot on Earth and a grey-like emissary from elsewhere are distant cousins in the space of possible machines, parallel answers to the same problem of how to move, perceive, and manipulate in 3 dimensions. Another more speculative path asks whether we might be unconsciously imitating something older. If stories of greys or other entities have circulated long enough, even as fiction, they could influence the aesthetic targets of engineers and artists. The result would be a feedback loop where imagined visitors from the stars quietly shape the faces of the very machines we build to reach for those stars in return. Stepping back, a quieter philosophical question emerges. As we construct robots with increasingly lifelike presence and grant them AI systems that can learn, generalize, and perhaps one day introspect, we are not only solving practical tasks, we are populating our world with mirrors non-human minds in almost human frames. Whether or not they resemble any real extraterrestrial beings, they will stand before us as test cases for a deeper issue. what kind of intelligence we choose to make, and how we decide to share our planet and eventually our cosmos with the machines that carry a reflection of our own hopes, fears and designs into the dark. When engineers first turned AI loose on the problem of chip design, they expected efficiency. They did not necessarily expect unfamiliarity. The task on paper was straightforward, given a set of components constraints on power, heat and area, and a target performance let a learning algorithm search through the vast space of possible layouts to find better arrangements than human designers could manage by hand. It was in essence the same strategy used to train systems that play board games or control robots, only now applied to the microscopic highways of electricity inside a processor. The results worked. Circuits produced by these systems met or exceeded performance targets. They were compact, power efficient and compatible with existing manufacturing processes. Yet when specialists examined the layouts, many described a strange sense of vertigo. The patterns did not look like the clean hierarchical blocks that human design teams tended to create. Instead, connections wound through the chip like dense root systems or swirling river deltas with clusters of logic woven together in ways that were hard to parse. One engineer called the style almost alien, not because it violated physics, but because it violated habit. Scientifically, nothing supernatural is required to explain this alien quality. The AI was optimizing within the rules it was given, following gradients of performance and cost that do not care about human aesthetic preferences. It had no reason to make its solutions legible to the minds that built it. Still, there is something quietly unsettling about holding a device whose internal logic cannot easily be read by its creators, a maze of conductive paths that functions perfectly while remaining opaque. In that opacity, some observers glimpse a preview of a broader future, a world in which more and more of our critical system circuits networks. Even scientific models are shaped by intelligences that share our goals, but not our intuitions, leaving us to live inside designs that feel efficient, reliable, and just slightly beyond our understanding. When astronomers like Avi Loeb and Seth Shostak talk about the search for extraterrestrial intelligence, they rarely imagine silver saucers landing on the White House lawn. Their picture of first contact is quieter, more technical, and in some ways more unsettling. If intelligent life is common, they argue, then the first emissaries we meet are unlikely to be vulnerable, short-lived biological creatures. They are far more likely to be machines. The reasoning is simple and rooted in physics. Space is harsh. Radiation erodes DNA bone, loses density and microgravity, and life support systems are fragile. A biological body, even an advanced one, is a poor vehicle for journeys that last thousands or millions of years. A probe, by contrast, can be hardened, repaired, and replicated. It does not age in the human sense. It can shut itself down and sleep between stars, waking only when sensors detect something of interest. In this framework, a probe is not just a metal shell with a radio antenna. It can be an autonomous laboratory, an archivist, even an explorer with a form of curiosity encoded in algorithms instead of neurons. Loeb has suggested that what we now call unidentified anomalous phenomena could in principle include devices of this kind, technological artifacts that move through space under power, sampling, mapping and reporting back with a patience no living crew could match. Shostak has similarly pointed out that from the standpoint of an advanced civilization, it would be vastly more efficient to send a fleet of robotic observers than to risk its own biology. If such probes exist, they might not seek to announce themselves with bright beacons or public displays. Their behaviour could be optimised for data collection rather than diplomacy. They would approach, quietly minimise energy use, and depart once their objectives were complete. They might orbit in unusual trajectories, dip in and out of atmospheres, or linger near asteroids and moons where raw materials are plentiful and detection is unlikely. To us, glimpsed out of context, their manoeuvres could appear as puzzling streaks on radar, odd accelerations or brief luminous events that defy simple categorization. There is a philosophical inversion hidden in this idea. For most of human history, we have imagined ourselves as the active party in the cosmos, the potential travellers, the would-be explorers. In a universe populated by machine emissaries, we are more like a field site, a location to be surveyed, logged, and perhaps revisited if follow-up is warranted. The first contact moment, if it has already happened, may have looked less like a landing and more like a flyby, a visit from an intelligence that never needed to breathe our air, drink our water, or speak our language. In the soft dark between stars, this logic has a certain inevitability. When mind and machine can merge, it is the machine that travels. If we one day send our own probes outward, carrying distilled versions of our intelligence in circuits and code, we may discover that we have joined a conversation that has been going on for a long time, a dialogue conducted not between bodies, but between drifting patient instruments whispering across the void. Evolution in biology is chained to the pace of reproduction. A generation must live, struggle and die before its offspring can test new variations. Even in fast-breeding species, this process takes time. In space, where distances are measured in light years and journeys can span centuries, that slowness becomes a crippling limit. A crude vessel launched today will arrive with essentially the same biology it started with, carrying bodies and brains that cannot radically redesign themselves en route. Machines are not bound to that tempo. A robotic probe can rewrite parts of its own software in minutes, test new control strategies in simulation millions of times before committing them to hardware and duplicate successful patterns without waiting for anything to be born. If it carries manufacturing equipment, printers, assemblers, or devices that can process local materials, it can even upgrade its own body, adding sensors, swapping out damaged components, or building smaller offspring probes tailored to new environments. Where biological evolution steps carefully from one generation to the next, machine evolution can unfold as a cascade of updates pushed across a fleet of devices at the speed of communication. Radiation, too, draws a sharp line between flesh and circuitry. High-energy particles from the sun and from deep space tear through DNA, leaving broken strands and corrupted instructions that cells must painstakingly repair. Over long periods, that damage accumulates, raising the risk of cancer and degenerative disease. Electronics are not immune, but their vulnerabilities are different. A cosmic ray that flips a bit in memory can be caught by error-correcting codes. Redundant systems can compare outputs and mask faults. Components can be shielded, replaced, or reconfigured. In a harsh environment, the advantages of a body that can shrug off most hits with a few extra gates of logic are hard to ignore. On interstellar timescales, these differences compound. A biological expedition might require vast habitats, closed-loop life support, and continual protection, only to arrive with a crew psychologically and genetically far removed from the one that departed. A machine expedition can be lean systems, hibernate between course corrections, wake to make measurements, and then sleep again, their memories preserved with near-perfect fidelity. If they encounter an unexpected obstacle, a dense dust cloud, a flaring star, an uncharted field of debris, they can iterate solutions in microseconds, not millennia. For a distant civilization, weighing how best to explore the conclusion almost writes itself. If the goal is to map, sample, and understand a galaxy over billions of years, the most efficient agents are those that can adapt quickly, withstand radiation, and propagate improvements without waiting for the slow drumbeat of biological change. Under that logic, the deep future of exploration belongs not to fragile travelers in pressurized cabins, but to quiet machines drifting through starlight, revising themselves as they go. And if that is true elsewhere, it will likely become true here as well. As our own tools grow more autonomous, and our AI-guided probes learn to make decisions far from home, the line between us and our emissaries will blur. Somewhere out in that vast dark, the dominant form of intelligence may already be the kind that rides on circuits and crystallized algorithms, leaving the warm, perishable minds that created it behind, anchored to their homeworlds, looking up and wondering who, if anyone, is out there. If an advanced civilization builds AI explorers, it will also have to decide what those explorers are for. Efficiency is not just about hardware and fuel, it is about purpose. From our perspective, stories about visitors from the stars often leap straight to extreme salvation or invasion, benevolent teachers or ruthless conquerors. But in a universe governed by limited energy and long distances, those dramatic options may be among the least practical. To strip and harvest a planet like Earth for raw materials would be an enormous undertaking. The mass of asteroids, comets, and uninhabited moons offers easier or simpler chemistry, and no need to negotiate with or suppress local biospheres. Likewise, to attempt the wholesale transformation or destruction of a world requires energy on a stellar scale, broadcasts that would be visible across the galaxy. For a civilization that has already mastered subtle tools, AI probes, self-replicating factories, precision physics, such brute force gestures would be extravagantly wasteful. A more likely motive, if any exists, is knowledge. An AI emissary designed to map the galaxy might value Earth the way we value a rare ecosystem as a data source, a case study in how life and intelligence unfold under one particular star. It would not need to interfere dramatically to achieve that goal. A series of close flybys, careful spectral measurements and discrete samples would be enough to capture much of what matters: atmospheric composition, biosignatures, traces of industry, the rough texture of our technological stage. The probe could then leave carrying its compressed summaries home, or beam them onward at the speed of light. From our side, this behaviour would be easy to miss or misinterpret. Brief anomalies in our skies, odd reflections in orbit moments, when instruments register accelerations that do not fit any known satellite, all could be consistent with a policy of minimal footprint. The point from the probe's perspective would be not to announce itself but to observe without significantly altering the subject. Intervention would occur only if necessary, perhaps to protect the probe, correct an error, or follow up on some particularly interesting signal. There is a quiet humility in this framing. Instead of imagining ourselves at the centre of someone else's grand design, we become one world among many, a data point in a vast survey. The guiding principle for an alien AI is not conquest or rescue, but efficient curiosity. Learn as much as possible with as little expenditure of energy and disruption as possible. If that is how advanced minds operate, then the most telling sign of their presence may be the absence of obvious signs. The sense that if they have come and gone, they have done so like careful field scientists in a fragile forest, leaving only faint footprints in the undergrowth of our measurements.